Okay. So let's see. So what we've done so far. Survived. We introduced a bunch of algorithms. Okay. We started from focusing a bit on the role of different loss functions, the square loss, the hinge loss, the logistic loss, and we essentially introduced what I would call the penalized DRM-like approach, so minimize the empirical risk plus a penalty. Then we moved on to, and in that case, we saw that in some sense computational aspects and modeling aspects are somewhat taken separately. And then we moved on to a situation where computations and modeling somewhat intertwine in a bit more, in a somewhat of a deeper way. We introduced what we might call the implicit regularization, but I hate it, so I'm calling it iterative regularization because it's the classical nerdy name rather than the fancy machine learning name. Then last class we introduced, here I use the keyword projection. You can call it sketching. We somewhat took a tour starting from PCA and landing on random projections. And we saw how somewhat the idea of dimensionality reduction, again, is very much related with regularization. In some sense, the idea of projecting the data in a lower dimensional space, either linear or non-linearly, can be seen as a form of regularization in the sense that it provides an approximate empirical risk minimization where the approximation is somewhat introducing a form of prior or bias on the kind of solution that we like. We mostly in this discussion deal with linear models, and we spend one class just seeing some tricks that allow to go from linear to nonlinear models using either a set of features or positive definite function, what you call kernel sometimes. Okay. But in what you've seen, in some sense, in this case, we actually explore three main, a couple of different coordinates. One is different loss functions. Okay. Then different way to design learning algorithm, penalization, iteration, and projection. But the thing that we kept fixed for now is what? In all these different techniques, in the end of the day, we were shooting for small norms. But not any norm, Euclidean norm, okay? So here I use this notation, but this norm is just this guy, okay? So that's the only norm we consider so far. But we've seen that this is somewhat the place where we put some, inject some, is one of the places where we inject prior belief on the problem, our somewhat idea that the solution should be simple in some sense. For us, simple has been in terms of small Euclidean norm, okay? Now, let me make one remark that we're going to make once and then we're going to close for all, but I think it could be interesting for later on when Sasha will discuss about, if he discuss about interpolations and other ideas going around this. Remember that the importance of this regularization is related to the class of models we consider. Suppose that you have a problem where you're dealing with 1 million points in one dimension, okay? And you choose to use linear functions. Linear functions don't do a lot of stuff in one dimension. Either your problem is really linear or you're not going to do a long way, okay? So in that case, it's not clear whether you're going to need extra regularization. And this story just keeps on going that way, right? So if your function class is very large, okay, then you might need some regularization, okay? And it might be that you're already doing it by choosing one of these schemes without noticing, okay? If your model is relatively more, you don't need much regularization, perhaps. What I'm trying to emphasize here is that in this story, we always kept here the linear model, okay? And then we assumed that it was large enough that something was needed. In practice, when you use this kind of stuff, the choice of features or the kernels you're going to use is also going to play a role, okay? And we haven't discussed that at all in this story. For example, you can say, I'm going to put here the Gaussian kernel, and then I'm just going to try to understand the role of the Gaussian width on this whole problem. Intuitively, the idea is that if you pick a very small a very small Gaussian, then you can have a lot of expression power in your function space, whereas if you pick a very large Gaussian, then you can only describe somewhat simple functions. Okay? We didn't discuss this stuff at all, but it's clearly it's important, because in practice, if you run any of these algorithms, you will see that there's going to be an interplay between the kind of regularization you do and the kind of function class you consider. Okay? A larger, a more complicated kernel might need more regularization than a simpler kernel. Does it make sense? I'm just saying this to say that I'm not going to talk about this, but perhaps once consider the situation where there is no regularization by the big kernel, then this story becomes important. Okay? This story is not unrelated to things like local methods such as Sparse and Windows or Nadara-Watson estimators. Estimates that are based on local averaging through some kernels, and then there clearly how much you average locally becomes very important. Okay? So I just want to say that I'm not going to talk about this. Okay? What we're going to do is that we're actually going to keep going our way. We're going to, for today, stick to this kind of penalized model. But we want to question the choice of this norm and actually consider other situations. Particularly what we want to consider is the situation where we make a slightly different assumption. We make the assumption that there is some form of sparsity. We want to understand the role of sparsity. Okay? Somebody already mentioned that when in all these methods, it looked like some of the principal components and the behavior of the function of interest on the principal components already somewhat introduced some notion of sparsity. We assume that the function of interest has most of its important components towards the principal components with large singular values. So we kill small singular values. Implicitly, we're assuming that something is not important. But now here we want to discuss sparsity more generally, not necessarily tailored to the principal components. Okay? So we want to understand what do we mean by sparsity. Broadly speaking, sparsity in common terms is that what we are looking for depends on a few building blocks. Okay? It doesn't depend on a lot of things, it only depends on a few things. At this level of generality, anything you meet, anything you cross in machine learning is based on this hypothesis. Okay? If you really have a super high dimensional problem, you need a ton of examples to learn. Okay? So if you're able to learn from a finite set of points, it means that the thing of interest has some notion of simplicity, and saying that it depends only on a few building blocks is fairly general. Here we want to instantiate this intuition in a precise sense. Okay? We're going to do this by essentially sticking to these kind of linear models. And for us, sparsity is going to translate for this kind of class of models in the assumption that the vectors of interest depend only on few of their entries. Okay? So the W's we're looking for only a small number of non-zero entries. The rest is zero. So in this sense, it's a sparse vector. It's a vector that is full of zeros. And we want to understand how to, what does it mean to make this assumption? Why would it be an interesting assumption? And how can we exploit it from a computational point of view to design algorithms? Okay? Is that clear? So we have a vector W. But we assume that only few of its entries are different from zeros. Okay? At most S. Notice that the very important thing here is that we assume that we're going to assume it's sparse, but we don't know how much sparse it is. So we don't know if it has 3 components or 5 components. But even more important, we don't know where they are. Okay? We don't know it's the first and the second components. We don't know where they are. Just know that somewhere in the vector there are some components. Not all of them are different from 0, but we don't know where they are. Okay? So this is the kind of assumption we're going to make. Make sense? Now, let's make one remark. We're going to mostly look at this. Okay? We're going to, from the sparsity world, doesn't go well with the kernel feature map world. Okay? The main reason is essentially the following. We can consider, okay, something like this. could consider something like this, okay? But we need to make a couple of observations. The first one, which is you just need to notice if you haven't thought about it before, is that sparsity, really the notion of sparsity that we just defined really depends on sparse on what, okay? So I called these two things W's, but they're really different. This is a W that is sparse on its, on these elements here, whereas this is a W which would be sparse on this phi j here. So you're sparse on some basis, okay? If you change the basis, suppose that now I'm going to take another, so this is a set of linearly independent vectors. I'm going to take another set of linearly independent vectors, phi jx, of the same size, okay? So psi j is another set of linearly independent vectors that allow to write the exact same function, okay? The fact that this is sparse, okay, bear no consequence of the fact that this might or not be sparse. In general, this will not be sparse, okay? You take a basis, you take a basis, let's say that's for the sake of saying this is a basis. You have a sparse linear combination of bases. You change the basis, there is absolutely no reason to assume that the vector is still going to be sparse. Does it make sense? Okay? Now, for this kind of norms, this was not an issue, actually. It was important that we choose a feature map, but if you choose another feature map which is equivalent to the first, it doesn't really matter. They kind of, everything here in somewhat was invariant to a choice of the feature map that satisfied this representation. Okay, essentially, it's the story that the L2 norm is invariant to the change of basis. Okay, you take a basis, you take the L2 norm, you change basis, you still have the same L2 norm. Okay, so if you change feature map in general, of course it matters. I can do it from one space to another. But if you take two feature maps that are equivalent in the sense that they give rise to the same kernels, this doesn't matter. Okay, as long as you stick to the L2, this won't make any difference. Okay, but if you do sparsity, it does make a difference because now you change the basis, now you're sparse on something else. Okay, so you can destroy your sparsity assumption by changing features. Do you see what I'm saying? Not really. Let me say it again, okay? I'm just saying the choice of feature always matter, okay? But suppose that you have two sets of features that are equivalent in this sense, that you can use them to write down the same function, okay? In other words, if thinking about kernels, you have two feature maps that give rise to the same kernel, okay? Then, if you use a scheme like this, using feature map 1 or using feature map 2, you're going to end up with the same result. These are completely, they will give rise to the exact same function. Okay? So far, so good? We are going to see now that if you actually consider sparsity, changing the set of features, even though they're equivalent in this sense, will matter. Because if this vector is sparse, when you go here, this vector might not be sparse anymore. Okay? So your commitment to sparsity on a set of features is much stronger. Because if you take another set of features, you may not be sparse anymore. Okay? Again, it's a small remark. There's nothing more than this observation. And I just want to remark the fact that sparsity is even more, is really married to sparse on a set of features. Okay? So the set of features that you choose is even more important than the one we chose here. Okay? Because if you get the wrong set of features, then you're not sparse. I'm saying also this because the role of sparsity has been ginormous in signal processing, because in signal processing you're dealing with low-dimensional functions where you know very well how to build good dictionaries. Okay, things like wavelets, curvelets, and all these different kind of dictionaries, frames, and so on. In high-dimensional world, we are not very good at building those things, and so typically we've been looking at just sparse linear models. Okay, we're not very good at building high-dimensional features. So I just want to remark that is an important point.
So I didn't quite get what you mean by equivalent of two set of features on basis.
I have a kernel. So I give you two definitions of what I mean by equivalent. I have a kernel, okay, and there could be two features that allow you to write that kernel, okay? The relationship with kernel and feature is not one-to-one. Given a feature, you have one kernel. But given a kernel, you have infinitely many features. For example, take any basis of the space, okay? So in that sense, okay? Or in other words, I give you a feature map, which is a set of linearly independent vector, finite feature map, set of linearly independent vector. You write the function. Now you take another set of linear independent vectors and you write the same function. Okay? This is another way. If you don't like kernels, this is another way to say what I mean. Okay? And again, for sake of this, think of two bases. Okay? That's it. That makes sense? And you can check. We're not going to do it now, but you can check that if you do this and you just do the usual L2 norm, it won't matter. You get the same function f. Okay? The w and beta will be different, but they give rise to the same f. If you start to make the sparsity assumption, this really goes away. Okay? We're not going to go that way. What we're going to do right now is that we're actually going to ignore the idea of features. You can consider sparsity over a set of features, but for the sake of simplicity, we're just going to use this notation. Okay? So we're going to stick to linear models, and we're going to assume that perhaps this was coming from some features, but it doesn't matter. We just simplify the notation, just sticking to that. Okay? Particularly, this will also mean that for us, infinite dimensional feature maps are gone. Okay? And you will see that the problem is that they will never come back. Okay? The moment you go to sparsity, there is really no natural way to go from sparsity is inherently related to considering parametric model. Okay? Models that are at most described by d or p variables. In other words, you'll see that we don't have something like the representer theorem in any form. Okay? We really have to live with the formulation where we have to work with the wj. Okay, fair enough. This was mostly remarks, so let's start the game. So if I consider this, we've seen that given data, in the end of the day, what I have to do is looking at some kind of linear system, right? This is the ND, this is N1, okay? And we are going to be particularly interested into the situation where the number of equation, so the N much smaller than D setting, okay? So we have many more unknowns than equations. Have we already discussed this before? For like 6 times? So there's no news here, right? So it's just that what did we do in this situation? What did we do? To find the solution, what did we do? Right, so among all the possible solutions, we consider the one with minimal norm. So we consider this the constraint, and then among all possible solutions, we consider the minimal norm. Okay? All right, but now I'm giving you another assumption. Okay? I'm not just saying I want a norm which is small. I say I give you a vector that have only very few non-zero entries. I don't know how many. Okay? I don't know where they are. But here I'm basically essentially the idea is that S is much smaller than D, that the number of non-zero components is much smaller. Okay? It could potentially, and it's typically going to be bigger than N, okay? But much smaller than D. No, sorry, the other way around. Is smaller both than N and D, okay? But it's especially the important thing is that it's much smaller than D, the total number of variables. That's an important bit here, okay? Now, suppose that I give you this assumption, and you have an infinite computer. How do you solve this problem? Again, the question is, I'm God. I put 3 numbers here. Then I don't tell you where they are. I give you this matrix. I give you this vector. And I ask you, OK, give me back the right vector.
Iterate for everything?
What do you mean?
So literally just, do we know that there are 3 exactly?
No, I don't know. But let's start.
But so can you not just pick any of the 3 to see how well they predict in your model and then just...
Right. So suppose that you know there are 3. You can take any triplets. OK? So you're going to take the first 3 columns and solve the problem. The second 3 columns, and then you take all possible triplets. Okay? But if you don't know if there are 3, you have to take all the single columns, solve the problem, then all the pairs, then all the triplets, and then that's why you need an infinite computer, right? Because this might take a while. And then you just say check on a cross-validation error what is the best possible solution. Sounds good? This actually sounds pretty reasonable, and in fact, when it turns out that if you only care about sample complexity and information theoretic term, kind of reasoning. This is actually an optimal thing to do. It might take a while, right? So the idea here is how can you do something more efficient? And if you settle for something more efficient, will it ever provide a decent solution? Okay. That makes sense? Now, turns out that what we just described, this exhaustive search, is what is called best subset selection. Is a classical problem in statistics. It's clearly a combinatorial problem. And it turns out that it can also be given a variational formulation. So what you just described is more like an iterative way to think about it, but it turns out that the same procedure is equivalent to actually solving a variational problem, a minimization problem, where you're minimizing not the L2 norm, but the so-called L0 norm. What is the L0 norm? The zero norm is actually not a norm, and it's just counting the j from 1 to d So in words, you take a vector, you go inside each entry, you check if it's 0 or not. Whenever it's not 0, you count 1. Okay? At the end of the day, you just count how many non-zero entries you have. Now, suppose that we introduce, this is another way of doing things, okay? And so basically, this, if you just read what this means, it basically says, among all the possible solutions, try to find the one with minimum number of non-zero entries. So it's another way to say, it's not a proof, but it's kind of intuitive, it's equivalent to looking for all possible subsets. So from an optimization point of view, it's also pretty clear why this problem is hard. Or is it? Well, so this is just a equality constraint, so it's not so bad. But here we went from the squared norm to this guy. What is this guy? It is essentially a sum of indicator functions. Okay, so you put an indicator function on each w, and if it's 0, you kill it. If it's 1, you sum it up, and then you sum everything. It's pretty nasty, right? Try to differentiate that with respect to the vector. It's crazy non-convex, and that's what gives rise to somewhat the hardness of this problem. You cannot just say, I'm just going to run gradient descent here. Okay, or maybe you can, but then you have to cross your fingers. Okay? So these are two formulations of the same story. L0 norm regularization or best subset selection are somewhat the brute force approach to variable selection. So the question is, how can we find approximate solutions, and are there ever situations where we have some guarantees that this solution will not be so bad? So we want to go from NP hard or combinatorially hard to computationally efficient, and we want to know how far we are from a decent solution from an accuracy point of view. There are essentially two ways of doing this, okay? If you've been sitting enough around MIT, you might probably say L1 regularization is the way to go, but I dare you to tell me that this is the most intuitive answer. Let's try to start from what he was saying, okay, which is this crazy exhaustive search. And let's try to hack it in order to make it less crazy, okay? We're going to end up with the other approach, which is what is called greedy method. Method that somewhat greedily builds solution in an increasingly accurate way, but with no guarantees that you will get an optimal solution, okay? So somewhat a coarse to fine approach. So what he just said is, I'm going to do brute first. I'm going to look, we're going to start from nothing and go up, okay? I start from the individual columns and solve the problem. Then the pairs of columns and solve the problem. Then the triplets and solve the problem. So clearly these become crazy, okay? But can you tweak it in such a way that you get something that you can at least run? And how would you do it?
Can you rank the features based on something like mutual independence?
You can do that. So she's saying, can I just rank the features based on something? And then, sure, but then you have to be sure that that thing that you're ranking is the same thing that is going to give you the best prediction of the output.
Yeah,
so you can do that. You could do something like that, but then you would have to know what is the impact of the mutual information ranking with respect to the other thing. And also, it's not clear how it's related to what he just said, right? I mean, I just want to take what he just said and tweak that into making it feasible.
Basically, you could do a stepwise search.
Right?
Start with one for each column, you do a regression and find out the one with highest prediction accuracy.
Yeah.
For each step, you add one column to that. And
Right.
That complexity is linear.
Right. So what he's saying is the key step is when you go from 1 to 2. Okay? The first step is the same. You look at individual ones. Then you want to go from 1 to 2. What did you want to do? Or I forced him now to be the person who wants to do this crazy thing, to look at all possible pairs. But what he wants to do is actually take, no, I'm going to fix the first guy to be the one that I selected, and I just get the extra good guy. Okay? So I don't look at all possible pairs. I look at all possible pairs where I fix the first guy to be the one that I already selected. Clearly now you don't have like something that goes as a square, but it's just linear. And how do you go from 2 to 3? Well, you keep the 2 that you already selected, and you just only add 1. That make sense? This is arguably the simplest way of doing things. You don't have to say convex relaxation. You don't have to say what cell 1. You just basically do something which is very intuitive. Okay? And this is the most basic approach of what you might call the greedy methods. Greedy methods are ways of producing solutions that are increasingly accurate, okay? And what we just described, we're going to write it down in a second, is one way of doing things, okay? Yes?
Is this has something to do with submodular functions or submodular set functions?
I'm sure it has, but ask Sasha is nodding. I mean, this is much simpler. So this is just a specific case where your function is just written on exactly one subset of things. So we're not submodular. I'm sure you can have a submodular functional interpretation of this. This will play no role in this description because we're just going to do inner product of things basically. You have something better to add, Sasha, to this embarrassing answer.
Indic did work on the greedy. Yes, they work.
All right. So I mean, submodular function is so for those who don't know, there's a much bigger boxes of like building function on discrete structures, okay? And this is just a super simple case for which you don't need to go to that kind of, you can, but you don't need to go to that kind of machineries, okay? It's actually what is related to, you might have heard this before, is, again, the name game is, this is called matching pursuit in signal processing, okay? And in statistics is a basic form of what is called stage-wise regression. In particular, this one is the forward stage-wise regression. Then, of course, you can go nuts and say, why do I want to go only forward? Can I go backward, forward, backward, in and out, more than one? We're not going to do that. We're just going to take this. We're going to go very simple. We start from 0. We add 1 at a time. We're going to do one twist because it's pretty obvious, okay? And that's about it. And these ideas have been resuscitated 10 years ago and studied extensively, but they go back it's been a while, right? So I think the 60s probably is the first time that when I remember seeing some references, but I'll bet that you can go even before. It's such a simple idea. You just basically have a multivariate problem, and you solve each individual univariate problem first, and then somewhat put an ensemble to get the global solution. Anyway, so let's write this guy, okay? Let's rewrite. So it's just going to take me 5 minutes to write this algorithm that we just explained because the notation is slightly annoying, but that's just to show it to you because it's simple and it's completely elementary. So there are essentially going to be 4 steps, okay? We're going to initialize. Then we're going to select. Then we're going to compute solution. Then we're going to update. And then we're going to repeat, okay? So this is going to be an iterative procedure that runs from t steps, from 1 to t, okay? We see what is the role played by t, and these are the first steps we do, okay? So what are the variables of interest is the indices of the important variables. This is going to be from 0 to d at most. We typically don't want to go up to d. And we're going to assume that at the beginning there's nothing. It's just an empty set, Okay? No variable is important when we start. We're gonna, so this is 0. Then we're gonna consider the initial variable, the initial vector of solution. So maybe let me put it up. Where do I put it? I put it low, so I'm gonna put it up. Okay. This is the vector of coefficients, okay? And at the beginning, we assume that it's empty. And then you'll see that we also need the thing which is the one that is slightly less obvious, which is a notion of residual, which in the first round is going to be the outputs. Let me give you the spoiler, which is going to be the only thing that is going to make the notation a little bit more interesting. The way you go in is that you say, okay, the first round, I pick the best variable, the individual best variable, by choosing the one that predicts the best the output. The second time, what you do is that you shave off what this first variable is able to explain, and you find the variable that can explain the rest the best. Okay? So you need to introduce the notion of the rest, which is going to be the difference between what the variables you obtain can explain so far and what's left. Okay? So that's why we need the notion of the residual. At the first round, the residual is going to be everything because we have selected nothing. Make sense? You select the variables, then you're going to go in and do the updates. Okay, so let me see if I didn't screw up my indices. So first of all, you do the select step. So let me run the select step. I write it the classical way. Well, no, let me not write it the selective. Let me do here one calculation. Okay. Let me call x hat j the jth columns of this matrix. Okay. So this is x, and this is x hat j. Make sense? Then let's write down exactly what you said, which is I want to say, okay, let's solve the problem with one column. Is this a vector or a number? Oh, a number, right? This is a column of size n. This is a vector, same size. And here I'm just looking at the way to scale this column in such a way that it's closer to this. That makes sense? It's a one-dimensional regression problem. Okay? So basically, you want to try to find for each j, you look and solve the problem with one variable. Okay? Yes?
Is the bias term included in or are we normalizing y?
Because you're afraid that you're going to have a scaling. Yeah, so now I'm not doing that, but that's a good point. So for the sake of this argument, we're going to assume that the columns have been normalized to have norm 1. Okay? If you don't do that, it means that the norm size is going to matter. Okay? In this way, you can measure the size of each of these coefficients in somewhat a common way. So again, if all the norms have size 1, okay, then every time you look at a coefficient, you can compare them. If you don't do that, in some sense, you're going to put presences of functions that have small norms, because then to obtain the same thing, you need a bigger coefficient. So for the sake of simplicity, let's assume that you, prior of doing this, you normalized the column to 1. I still write them because I want to show them, but you can assume that they're normalized to 1. Okay? Back to this. So this is solving the problem with each individual variable. Okay? The solution of this is equal to what? Well, you just have to take the derivative of this, set it equal to 0, but it's super simple because it's one dimension. So this is just going to be x transpose j y divided by xj norm square. Okay? You just take the gradient of this, set it equal to 0, and this is what you get. Make sense? All right, so but we need to complete the select step. What do we need to do to complete the select step? We solve the problem for each individual variable. Now what do we want to do? We want to pick the one with smallest error, right? This means that we want to take these we want to take this VJ, plug it back in, compute the error, and take the VJ that gives me the best of this thing, right? I'd love some nodding here so that I can know if I can keep on going because it's trivial or you want to kill me. I'm assuming that it's trivial for now. So you plug it back in here, so you're basically solving for each one of them. You plug it in here, then you want to take the J that gives you the best of this, okay? If you take this expression and plug it in here, you get that this thing can be simplified a bit, okay? We're gonna skip the calculation and hopefully not make a mistake, but you're gonna get y square, and then there's going to be some simplification, and you're going to get okay. So this, you take this VJ, you plug it in here, take the square, see what you get. I skip one step here, and this is what you get. You get y norm square, and then you have that there is some cancellation between the square of this and the mixed product of the two, and so this is what you get, and I'm skipping this, okay? Sounds good? Not anything interesting going on here. I'm writing this just because this is the way you typically find it on Wikipedia, which is the source of all knowledge, right? So when you look at Wikipedia, then you say select J that belongs to 1D that maximizes minus x, minus xj transpose y xj square, okay? So if you see that equation, now you can do it, you can look at it in two ways. You can say, okay, I went this way, so I know that that's the way to just say, find the solution that solves the least square problem individually with the smallest error, okay? If you prefer a more geometric interpretation, you can also see that this is essentially some form of projection correlation, okay? So you basically say, I have all this vector x, and I'm going to project y on this vector x and find the one that is more collinear to it, okay? That's another way to see what you're doing, okay? This is just the best possible one-dimensional projection of your vector x. That make sense? That's it, okay? This is the most complicated thing in this story, and that's why we start here. It's completely elementary. Without the minus, of course. Yeah. So it's minimum of this. This doesn't matter. So you want to minimize this, which is equivalent to maximizing the same thing without the minus. Thanks. All right, I cheated a little bit here, okay? Because this is the first round, okay? This is how you do the first round. Why? Because I'm comparing to y, okay? But this is just the first step, okay? So what you want to actually write down is that now you want to iterate this, okay? Yes? Why is it what? I didn't get it. So you think why there is a square? Because unless I made a mistake, there is a square. Because it's the square here. So the square is here. It comes from the fact that when you take the gradient, you get x transpose j that multiplies x transpose. So you have xj transpose multiplied xj, and this gives you this. You see it? Let's check. Since you were, so I'll write it here and then we'll delete it. Okay? So you get xj transpose xj v minus y equals 0. Right? So this x transpose y gives you the numerator, and this x transpose x gives you the denominator, which is getting the norm square. That make sense? Sorry, I don't. Right. So also, I do this just because I want to show it to you. But again, in all this story, that guy is 1. Okay. So we already took care of this, making it 1. It's just that I don't want to delete terms along the way. So, but let's assume that we have to take the norm to be 1, and it's done once and for all. So it's there, but it's not there. Okay. It won't matter. Okay. Okay, so that's fine. Then how do we compute the, we select this guy? So let me first do the first round without updating the residual. Let's do the first round, and then we just change y with the residual, because that's not very interesting. So let's first write down the way you update the solution. So you're going to say, in fact, notice, okay, so what you do is that you say, okay, w I is going to be equal to wi minus 1 plus, this is one possible way to write things. So what is ej is the element of the canonical basis of size d. So it's a vector that is all zeros, and it only has 1 at the jth position. And by multiplying by this number, I enter the number vj in the right position. So this means essentially that I'm going to start from a 0, 0, 0, 0, 0 vector. Then I find out my vj. I put it in the right position. And then I'm going to, by adding them, I'm going to populate this position. OK? I'm going to get this guy. Then at the second round, I found another vj, which is here. I sum it up, and now I populate this other dimension. That makes sense? Of course, you have other ways of writing it. This is one way. So this is just the canonical basis, and it's just a way to populate the right location of the vector. OK? Well, and then you just take the set of active variables, and you add the one that you just found. And that's it. OK? Then you go back and start again. The only thing that I didn't tell you and I should do is that I have to tell you what we do with the. This is the first round. How do you do the second round? It's the same. You just have to also define Ri to be Ri minus 1 minus x hat wi. Sorry, let me put this up because I did it up before. Okay, so I runs not on the components but on the cycle of my iterations. Okay, so I start from 0, I populate, I update the active set of solution, and then I define the residual to be whatever we had before minus the extra, that you got out of this. Okay. That's it. And so in this thing here, everything you need to do is to replace this guy with r minus 1. Doesn't matter. OK? Yes?
What is the exact WI?
It should be. You're right. So this is the version where I put here what I was thinking about. This should be it. So you can write it. So you can either write it like this, in which you reshave everything that you found before, or you can write, like this, or you can write it like this, and then you have to write like this. Okay. So either you reshave everything all the time, or you just take off the last bit from the previous residual. It's the same. Of course, I mixed it up. Okay. And I think it's mixed up also in the notes, in the slides, so I'll fix them. Sounds good? So I don't want to spend more time on this because there's not really a lot going on. It's just this, OK? We want to make just a couple of observations. So the first thing, this is the first of a family, OK? It's the oldest, the simplest idea. As I told you, there are many, many variants. I think the one variant that is worth mentioning in terms of the next one over is the so-called orthogonal matching pursuit. And I'm not going to write it down. I'm just going to tell you what it is in words, okay? Because it essentially is exactly the same thing up to here, but then it just changes in the way you find the solution at the current step. What do you think it could be? How could you modify this to be a little bit less wasteful in the way you compute your solution? So you select the variables in the same way, but when you need to update, you want to be a little bit more less wasteful. So what is the big waste here?
You don't use VJ, you will compute it using the whole selection.
That's what you want to do, or that's what we're doing now, you're saying?
That's what we want to do.
Right, so what he's basically saying is, here you select the best variable, and then you compute its coefficient. Then you select the second variable, and you compute its coefficient. But the first variable never knew that its soulmate was going to come, a few iterations later. And this counts for all the others, okay? So basically, you're literally just solving many univariate problems completely separately. So what could you do? Well, you could say, okay, when I selected two variables, I'm going to compute the second variable and the first variable by just solving the linear system corresponding to the two columns that I selected so far, which is exactly, I believe, what you were suggesting. And you can keep on going that way. Then you go from 2 to 3, and then you're going to select this, this linear system that correspond to the 3 columns you selected so far. So these become orthogonal because you can check that essentially you get better use of the geometry of your columns this way. Okay. It's better in any possible sense. Intuitively, mathematically, you can prove it. You pay a price. What is it? Pretty obvious. You have to solve a linear system every time, and it gets bigger and bigger and bigger. Whereas here, it's just linear every time. Okay. So this, of course, is super fast. Fair enough. So I'm not going to write it down because it's mostly, you have to find a way to just define the submatrix, and then that's it. And then the rest you can just do exactly the same. Okay. I guess the other question here is, where is the regularization parameter? Is where you stop, is the number of iterations. Notice that I don't take out variables after I select it. So in principle, I can select a variable twice. Okay. But what I do is that the more steps I take, the more variables I take. So here, the equivalent of something like lambda, okay, something that enforces more simplicity, is the number of iterations again. If you take few steps, it means that you take a very simple model because you're starting from the 0 vector. If you take more steps, you're introducing more variables, and in principle, you can fit better. Okay? That make sense? So how do you choose it? Well, the same way you choose lambda or whichever regularization parameter you met before. Okay? And again, not because this is the best thing, but because we're not going to discuss this at all. Cool. Arguably, this is the first thing that comes to mind if you start from the brute force approach and you want to fix it. Okay? Clearly, this you can run on your computer. In fact, you can implement it so fast that it's almost tempting to do it. Of course, you can ask the question how much you're losing, and we're going to discuss later on, if I have time, a comment about this. Okay? But for now, this is just an obvious approximation, and the name greedy method is pretty clear. Any question about this? Yes.
So let's say if I'm doing it on features and my features are highly correlated with each other, so then there will be some problems there, right?
Yes.
You always select correlated features.
Yeah, so what he's asking is, suppose, let's take a chance to actually say, why do you want this stuff in the first place, okay? So, and maybe you can answer that before I answer his question. Why do you care about doing this, okay? Why this story is interesting? There are a number of reasons depending where you come from. All right, so if you have been sitting in a stats department enough, you say, n is smaller than d. High-dimensional statistics. I cannot learn a model that is dimension d if I have only n points. There must be something going on. I have to make some assumption. There you go. The true number of unknowns is smaller than n and much smaller than d, so I can still maybe do something. Okay? And definitely this is the point of view that has been taken. And if you see high-dimensional statistics, oftentimes start exactly from this and keeps on going. All right? Assume that you've not been sitting for a minute or raise your hand if you've not been sitting in a stats department and you see this stuff. What is the other reason why you might want to do it? If you're sitting, for example, where I sit, which is more on the machine learning side, well, I've been working under this assumption even before. I would just put in a squared norm, okay? I don't know if it was correct or wrong, but I don't care. I just use it, okay? And then I see what happens, and it was still fine, okay? So I'm not losing the fact that I cannot solve the problem. I'm losing the fact that I don't use sparsity. Okay, maybe that's a bad idea, but what do I really gain as a machine learner by using sparsity? One thing could be computation, for example. Again, if you're a machine learner, you spend some time in a computer science engineering department, and if you run things forever, it's annoying. And then maybe if you can compress things, if you just find out that what you need are just 2-3 variables, then you can just carry them on. Maybe it's going to take you a while to find them, but once you find them, you don't have to carry a full vector. You just carry 3 dimensions, okay? And if your data is 1,000,000 by 1,000,000, this can be interesting. So compressing, achieving better computation is one. What else? Boom, there you go. That's my favorite word. This story, I think, oftentimes in machine learning is a synonym of interpretability, okay? Whatever we did, we can provide an answer, but if somebody asks, okay, what was important in providing the answer, then you have to go back and say, well, I don't know, But here, of course we settled for a pretty simple problem, but then we can say, if feature 1 was important, that's what matters, okay? Because I can just go in and look at that. Of course, you're making an assumption that things only combine linearly, which is huge. But at least you have a very clear path towards interpretability. Okay? So these are the 3 different reasons. I'm making this small preamble before answering this question because now, depending where you're at, the question of correlation can be more or less important. So what he's saying is, what if I have a bunch of columns here that are very close to be collinear? Well, I don't know, but computationally what's going to happen is, especially when you have error, is that when you start to compute this kind of inner product, you're going to have a bunch of things that are very similar, okay? And you're going to have instability, you're going to have redundancy in what you get, you got a lot of problems, okay? Now, if you only care about reducing computation and just kill stuff, maybe this is not so important. You just find any hack around it to keep on going, okay? If you don't care about interpretability, you only just care about reducing the size, you can do any kind of pre-screening to kill, for example, correlated things. I don't care. You're in the kind of throwaway stuff mood, okay? Again, imagine that I take a kitchen sink approach where I just shove together a lot of features. I don't know which features are important, so I put a lot together and then I try to reduce the size of them. I don't know, give me another way to throw them out. I'm happy. So pre-screening correlation and throw them out, great, okay? What if you actually want to do interpretability? Well, then it's a different business, right? Because if it so happened that 2 correlated variables are extremely important, you cannot just say, I'm going to throw one away. I mean, if you go to a doctor and say, oh, it's this gene or the other one, but I don't know, this one I throw away. He's not going to be very happy about it, okay? So that's a problem, and we'll see that you need to fix it. These guys don't work well with correlation, and essentially you have to tweak things around a bit. And there are a number of ways of doing it. If I have time, I'm going to tell you about it. The spoiler is that one way to do it is combine the L1 norm and the L2 norm, okay? The theorem that says when this works essentially prevent correlation out front. It's basically saying this is a good idea if there is no correlation, or if the correlation is low enough. Okay? So in some sense, this guy will work only if there is no or not a lot of correlation. Okay? Cool. Other comments?
So should we use this or PCA?
Good question. Anybody? The question is, you gave me this, and this reduced the dimensionality of your final predictor somehow. Okay? But we also learned PCA for regression 3 days ago. What day is today? 2 days ago. Okay? Which one do you want to use? Think a second about it. It's actually an interesting question. I saw it.
Depends on if you care about interpretability versus performance.
I guess it depends on the assumption of the space we are talking about. We believe the sparsity exists in the principal component. We could use PCA as classic regression. But if we believe the sparsity exists in the IX,
Yeah, so what he's saying is, well, it depends if you care more about interpretability or not. There is no reason why to think that this guy, in terms of performance, this guy or PCA is going to work more or less well. Definitely, it depends on a bet that we're doing that we cannot test of which prior assumption is more correct. Sparsity on the PCA or sparsity on, say, in this case, the canonical basis. Okay? But what he's saying is, if you go the interpretability path, which is also related to what you're saying, one is not going to give interpretable stuff. If you look at the first principal component, it's a feature extracted from the data, which is a linear combination of every columns of this. So it selects a linear combination of all of them. The second principal component also. Again, suppose that this guy have a meaning. So these are genes, gene expression data. Okay. Then I want to know if this guy is important or not. I don't want to know that there is a combination of this guy and 5 billion others in different quantity that is important or not. So the big difference is that you're just saying these guys are going to actually give a more interpretable solution if the identity of the features matters. If it doesn't matter, if you just want to reduce the size of the model, it doesn't matter. You can take one or the other. Of course, depending on what God chooses to put as a prior, it can be one better than the other, but you don't know in a way. You have to try. We are using the Ys. But also in PCA. So again, depending what you mean by PCA, okay? So if you do PCA, and you don't look at the Y, you're right. But if you do the PCA that I told you the other time, you do PCA. So suppose that you do PCA, but then you choose the number of components you want to pick based on the empirical risk minimization, what we call principal component regression. Then you're using Ys both times, and it's just that you're looking at different assumptions. That make sense? And again, in one case, you take interpretability on the variable. In the other case, interpretability on the PCA, which is arguably less interesting. OK. Okie doke. Let's move on. So this was the greedy methods. Yes?
Before you erase, I think there's a square. So when you plug in the value of
Here.
there should be a square on the.
This guy. Yeah. Yes. Sorry, I thought you didn't like this one. So I concentrated on the. It's distracted, so it's OK. Here. Yeah. We fixed it. He's right. So the problem is not this. It's this. There is a square here. And it comes from the fact simply that when you plug this in here, you get the x transpose y squared. OK? Say again? Yeah, the units are happy now. Sorry, I was looking at the one below, which I was sure was right. And I didn't notice that I forgot the square. OK. So it should be fine more or less all places. This one is this one. No, sorry. Now it's Sasha's fault, so I don't care. Let's move on. Let's move on because otherwise, L1 is the best thing ever, so we have to talk about it. All right. Okie doke. So here, what we're gonna do, okay? We're gonna say this is the I don't like math way of doing things because the most evolved things is squared that I can make a mistake with and inner product. But here we're actually gonna be fancy. We're gonna say, you know what? I don't like this either. It's too complex because it gives rise to a non-convex problem. So let me actually replace it with a convex problem. Okay? What is the L1 norm? The L1 norm is just the sum of the absolute value of the coefficient rather than the sum of the square, okay? And a way to think about it is before the L0 norm is I look at the vector and every time I see something that is non-zero, I count 1. Here I count the absolute value of what I saw, okay? The absolute value, the indicator function looks like this. The absolute value looks like this. It's convex, we're happy, okay? Of course, again, you can say, okay, how much am I going to lose? But you can also say, okay, it's convex, but still is not that obvious. Again, consider this formulation, but we can also consider here this formulation. Again, let me restrict ourselves to least squares, just because it's simpler. but you'll see easily where it matters, okay? Again, the novelty here is in this little one. Again, you can ask the question we asked before, okay, I'm replacing the original problem with the new problem, how much I pay from that perspective, but you can also just ask, okay, but how do I solve this, okay? And why would this lead to sparsity? If you take it from this point of view, the difference between the two seems minor, right? It just seems to be just a small exponent inside the sum or not. So why would this make such a big difference? So this is the two questions we want to understand. So question one is, why does L1 leads to a sparse solution and L2 doesn't lead to a sparse solution? And we're going to look briefly at the geometry of the problem. And if time permits, we're going to ask the second question, which is, how do you solve that problem over there? Okay. So to answer the first question, the one about the geometry of the problem, we're going to stick it to this constraint formulation. Okay. Those reasoning can be also developed here, but this is just simpler. And the idea here is that we want to now write down a graphic way to solve this problem. We have to use some fantasy here, because to draw it, I'm not going to go above 2 dimensions, okay? Now, we're looking at the situation where there are multiple solutions, though, okay? So we need not just one solution in W, but we need to assume that there could be multiple solutions. And in this case, we don't have much room because we just have 1 dimension. So either there is 0 solution, or 1, or if you have multiple solutions and have to draw them, what they will look like. Well, let me remind you, this is called linear system. Well, there will be just a line, okay? The set of W that satisfies the linear system will just be a line, okay? This is the case where I have redundancy, okay? If I am n is smaller than d, I have more than one solution, okay? And this would be it. Okay, so this is given by the constraint, and then I have to find among all the possible L1 norm, the one W that satisfies the constraint. Do you know what is the shape of the L1 norm? Well, the L2 norm looks like a circle. The L1 norm looks like a diamond. Diamond, there we go. Now, basically, this means that graphically, to actually find the solution, what I'm going to do is that I'm going to inflate the diamond until I find a vector that lies on this. Then I can keep on going, but then it will not be the minimal one. Okay? So I stop when I find the point of this, then intersect that. Where is that going to happen? Here. Why this is beautiful, and we can do the like, oh. Because this point is together? It's sparse, right? Oh. Now, if you were doing the L2 norm, I'm going to do it here because I cannot do them of the same size. Where they go? Well, that's clearly a ball, Giotto. So where do they touch each other? I don't know, not here and not here. Okay, somewhere here. Okay? Well, maybe closer because I suck, but that's the point. Okay? So you see, they're going to be smaller or bigger, but they're not going to be 0. Okay? And in this simple picture, which just stands on the fact that we realize that the set of the general solution of this problem is a linear space, and then it's going to intersect in this simple case the L1 ball in one point and the L2 in a vector which is sparse, and the L2 in a vector which is not sparse. It's pretty generic. Okay? Now you can ask a complicated question, which is, what if the dimension is bigger than 2? Well, then this is not going to be a line, it's going to be a hyperplane, and this is not going to be a simple square, it's going to be a polyhedral thing. And then you have go nuts with nice math in high dimension to realize that this take-home message still goes through, okay? But that becomes complicated, and that's beyond the point for us. But this is the main reason why, if you look at the geometry, okay, this is basically the geometry of the problem, then the geometry of the problem is basically So the geometry of sparsity is this picture here, okay? And this answers the question we wanted. Why this way of they're both way of relaxing. You go from L0 norm to L2 or to L1, but only one of them is going to give you sparsity, okay? That makes sense? Yes? Yeah, you project. Yeah. So as I said, so what he's asking is, what if this constraint cannot be solved, satisfied exactly? Well, typically what you do is that you relax it. And then if you want, this is the Lagrangian formulation of this kind of problem. And you're right. You can also, as I said before, we just stick to this because it's simpler to think about it, the one where you have the exact constraint. But essentially, the same reason is going to go through also in the case where the constraint is not exact, or when you consider something like this. It just becomes a bit more complicated, okay? And it's totally beyond, sorting out the details of this is beyond the point in our discussion. Yes?
What if that function is not linear?
This function is
Yeah,
linear.
yeah, that's not a line if it's not a linear
No,
function.
it is a linear because it's the solution of a linear system.
Okay. But I guess my question is whether this sparsity will also be applicable when it's not a linear system.
But this is not about this. You have to go back to the beginning, and basically you have to tell me what you mean by sparsity of a nonlinear function. Okay? And again, this is an important question, and the more you think about this story, the more you realize it's important, because basically you can say, okay, I use feature. Sure, then you're going to be sparse on the features. Okay? So again, suppose that you have, again, genes that matter. Okay? You're not going to be sparse on the gene. You can take the square of a gene, the cosine of a gene, and you can be sparse on that. But it's a different story. So if I have time, and I'm happy to discuss it all that, there are a couple of ways to extend sparsity to consider nonlinear models, but there is no like straight-on way. For L2, you just go to kernels and that's it. For this guy, the story is a bit more complicated. There is no obvious way. Okay. Okay. Anything else? All right. So what's left to do? This gives a sense of why sparsity L1 is sparse. Okay. It doesn't quite give you a sense of how you solve that problem. And so we can ask 1 second how hard it is to actually do computation on this. Okay. So you need to solve this problem here. Let's stick to this variational formulation because it's a bit easier to discuss. Okay, how easy it is. We are quite happy, not excited, but quite happy. Let's see. The first term, it's nice. The second term, così così. Why? It's nice because it's convex. It's not so nice because it's not differentiable. It has a kink. It has a point where it's not differentiable. All right, but we're good because we already discussed this stuff, right? We have something which is convex but not differentiable. So if you try to do the gradient, you can do the gradient of this, but here you cannot do the gradient, okay? But what can you do? Subgradient, which is what that thing that in the end of the day you just take the left derivative and you keep on going, okay? Sure, you can do that. You can do that here, and it's fine. And it turns out that that's actually a bad idea. Why? Because this is nicer. This is actually turns out that you can write 10 years of papers by staring at this enough. Because it's not just any convex non-differentiable function. It's what you might call a composite problem that has a sum of a convex non-differentiable term. So this part is really minimal assumption, but this guy here is actually differentiable. Okay? Now you can ask, okay, can I do something with this? Okay? I know that I have two parts, the differentiable part and the non-differentiable part. Can I exploit this special structure to do something better than just subgradient? And the answer is yes. Turns out that whenever you have something of the form where this is everything is differentiable and everything is convex, then there is some nice set of techniques from optimization that you can use that is broadly referred to as forward-backward splitting and related to proximal methods. The notation I used. So proximal methods are nice because they say yes.
That the sum should be just convex, or both of them also?
Both of them are convex. Yeah, if you want. Yeah, I was lazy, but if you want, let's write it this way. Okay? And I'm always going to assume that they're continuous, okay? You can be fancier, but I don't care. Now, it turns out, so the story starts a bit complicated, but it turns out to be extremely simple. And by doing this, you gain the fact that these kind of techniques, again, forward, backward, splitting, related to proximal methods, they're kind of nice because in some sense what they do is that the forward-backward splitting part essentially comes from the fact that you're going to decouple the contribution to computation of the differentiable part and the non-differentiable part in a very intuitive and easy way to remember. Okay? And then the proximal methods come from the fact that the differentiable part is going to contribute in an extremely easy way, but the non-differentiable part is going to contribute in a slightly more complicated way. Turns out that in practice it's simple, but the definition of the object itself is a bit more complicated. Okay? So I write it in general terms. The proximal operator splitting, the forward-backward splitting method essentially works like this. So you compute the gradient of the differentiable part, okay? And there is no non-differentiable part in sight. But then here there is a map. Here. The proximity, this is called the proximity operator. And it's a map that takes a vector and returns a vector. Okay? So it's a non-linear operator. It's not a functional. And it's defined this way. The what?
Don't pay taxes.
Okay. So let's look at this guy for a minute, okay? So here, there's nothing going on, okay? Just look at this. This just says an important fact, which is that there is a class of method that has this name, where you can write an algorithm where the differentiable part is only going to contribute for a gradient, a simple gradient. But some interesting thing is happening because of the non-differentiable part. Because the non-differentiable part is going to contribute a non-linear operator called proximity operator. If you want, in your head, think of it as something like a projection. Okay? So if this was a projection, this would be projected gradient. Sasha briefly mentioned that if you're looking at a constraint, you can just, if you have constraints, you can just take the gradient and then project on the constraints. Okay? This is not always, almost always something like a projection, but the definition is actually written here. Now, let's just stare at the definition 1 second. The definition is simple, yet a bit puzzling the first time you see it, because first of all, you don't have a closed form expression. It's a minimization problem in its own right. Okay? And in the case of least squares, it will look very similar to the one we started from. What is the main difference? Well, there is a 1/2. But the main difference is that really that there is no, there is no x, okay? That there is no matrix x. There is an identity here, okay? You learn in the exercises with your own sweat that actually makes the big difference, okay? So it's very similar. We are replacing an optimization problem with another optimization problem, okay? You should think of R as del 1 norm here. Okay, fair enough, yes. Argmin. Thanks. Okay, it's the vector that minimizes that. Okay, you give me W, I compute that thing, I minimize, and you get back a vector. Thanks. Okay, so remember that in your head you also have the subgradient as a counterpart of this. Okay, so why would you want to use this or the subgradient? Well, I can tell you. There is a theorem that says that this converge as fast as gradient descent for a constant step size, that you choose the same way you choose the step size for gradient descent, looking at the Hessian of the differentiable part. If you remember for the subgradient, what you can do is that you can either do averaging and look at an upper bound, or what you can do is to look at a decaying step size. Okay, you typically need this decaying step size for the subgradient. And the rates you get, we didn't discuss it, but Sasha showed it to you, is something more like 1 over square root of t. Here, what you get is that you get a faster rate with a constant step size. So this, even the proof of convergence of this is essentially the same as gradient descent. Okay? So that's good news. There is kind of an elephant in the room right now, because I replaced an optimization problem with an optimization problem that I have to solve every time I run an iteration. So this better be something that I can solve really well, right? Otherwise, every time I do a step of gradient, then solve an optimization problem, and I'm going to step, and that sounds crazy.
Isn't that R being instead of lambda?
It is. Okay? So the question we want to ask is, are there good examples of R? Remember that I wrote E and R because you might want to think of this as the error and this is the regularization. So the question is, are there good examples of R that I can compute in closed form? And the long story short is, anything that looks like L1 is one such example. Okay? So the proximity operator, in the particular case where here I put L1 norm, has a very nice form, a closed form that you can write immediately. Okay? Oh no, immediately making a mistake, so let me take a look. So it's a nonlinear operator, but it acts component-wise. Okay? So I'm just going to tell you how it looks on the jth component. And it looks like this. You take the jth component, you check if it's bigger than lambda, and if it is, you let it go and you decrease it a little bit. Let me finish writing and then we comment on it. So if you put del1 norm, you can actually show that you can compute this solution of this problem in an extremely efficient way, and it's just a soft thresholding operator. In a linear map that takes a vector, look at each entry, and essentially says the following. If the entry is small enough, I'm going to set it equal to 0. Otherwise, I basically let it go almost unchanged. This operator look at the jth entry of the vector, and if it's between minus lambda and lambda, set it equal to 0, exactly equal to 0. Okay. If it's big enough, it decreases a little bit. If it's small enough, it increases a little bit. Make sense? It's not too hard to prove that this is true, and in fact, you're going to do it. But what we care about right now is that this is actually provides a solution which is sparse at every iteration. Every time, if you look at the subgradient, it won't give you solutions that are sparse at every iteration. But this does. What you do is that you run gradient, and then at every iteration, you set everything below this threshold to 0 exactly. So suppose that you ask, why is L1 leading to a sparse solution? This is another way of seeing it, because you can solve it with a solver that is going to kill components as it goes. You can actually compute, if you want, the proximity operator for L2, and this will just be renormalizing by the norm of the vector, okay? So you take the gradient, and then the projection on the L2 ball is just normalizing by the norm. So no way you're going to get sparsity out of that, okay? That's it. So we found a way to solve it computationally, I just described a way to solve it computationally. They take advantage of the specific form, okay? By writing something which is something like a projected gradient, where rather than a projection, you have to compute a proximity operator. And it turns out that the proximity operator can be computed in extremely fast. The corresponding algorithm sometimes is called ISTA, which stands for Iterative Software Shielding Algorithm, okay? I close it here. Let me just say two things, and then I'll let you go. First, this is the tip of the iceberg of work that people have been doing in 10 years in two different directions. One, as a modeler, you say, okay, L1 is nice. It looks like it has some properties. How general, okay, and I generalize it somehow, okay? And there's a whole domain of structure sparsity where you say, you just define building blocks a bit different. For example, group of variables, okay? Overlapping, non-overlapping, and so on. Then you can say, well, what about if rather than vectors, I want to deal with matrices or tensors? That's another way to go, okay? And if you want, for each of these, you can play the game of understanding the geometry of the problem, but you can also play the game of understanding what these proximity operators are and if you can compute them in fast way. So, and in the past years, we had a couple of classes about these kind of things. A last direction where you can go is that you can try to combine this with kernels, and essentially this leads to what is called multiple kernel learning. Okay, so multiple kernel learning is a variation over this, where in some sense you look at a different form of sparsity where you try to be sparse over a set of kernels. Okay? And again, if you're interested in this specific line this year, there's nothing about that, but you find it in both the notes and previous year classes. There are videos and so on. Okay? This is about it. So, finished.